In this lecture, we are going to discuss Newton's three laws of motion. These laws can be paraphrased in the way that I've written here. The first law is about inertia. It's just a statement that inertia is a thing. The second law is the exception to the principle of inertia, which is that the motion object will change when there is an external force acting on it. And the final law is a statement that the internal forces in a closed system are always balanced. So, this first law, to do with inertia, is related to the idea that an object in motion will remain in motion unless acted upon by an unbalanced external force. Prior to Newton's time, the belief was that for an object to stay in motion, there had to exist a force that maintained that motion over time. And the reason this perception existed is because almost all objects which are moving are subject to friction. And friction has a tendency of bringing objects to rest relative to the surface they're sliding across or the medium they are moving through. But if you are able to remove sources of friction, then you'll see that the principle of inertia does hold, and this principle simply states that objects will maintain their motion at whatever constant velocity they have until a force acts on them, external to themselves. And once a force acts on them, the second law kicks in, which says that these external forces cause the objects to accelerate. Now remember, acceleration is the rate of change of velocity. So all we're saying when we're saying external forces cause objects to accelerate is we're saying that the external forces change the motion or they change the velocity of those objects. Finally, Law 3 is essentially the statement that objects cannot make themselves accelerate without an external force. So the internal forces of an object, this would include like the molecular forces that hold the object together. These cannot cause the system as a whole to accelerate from within it. The only way to cause the system to change its motion is for a force outside that system to act upon it, or for the system itself to break into multiple different systems. So for instance, it would be possible if you and a friend were holding hands, the two of you could count as a single system. But then if your friend pushes you away from him, then he could make himself move by externalizing you, right? By making you an external system to himself. But still, the center of mass of the two of you would stay with whatever motion it started with, regardless of what your friend did, because the system as a whole cannot make itself accelerate. So that's all I have to say about that. Let me get rid of that circle that I drew around that. I guess I can't. Okay, so next. So let's dig into the principle of inertia a little bit more. So the principle of inertia is the statement that an object in motion will stay in motion unless acted upon by an unbalanced external force. And as an equation, what this is saying is if the sum of the external forces acting on the system add up to 0, in other words, they cancel each other, then that means that the acceleration will be 0. The motion will not change. If the acceleration is 0, that also means that the forces must be balanced. So these are identical conditions. You can't have one without the other. That is Newton's first law of motion, and this equation at the bottom is the equation form of that law. When the external forces... Okay, so this is for Newton's second law. And this says that when the external forces acting on a system are not balanced, then the system will change its motion. It will accelerate. And so the formula for that is the total sum of all the forces acting on the system is going to equal the mass of the system times the acceleration of the system. And so we can determine the acceleration by dividing the net external force by the mass of the system. So this is all the external forces contribution, and that creates an acceleration, but it's not equal to the acceleration. The mass determines how much acceleration we're going to get from a given amount of force. And finally, we're at Newton's third law, which has a kind of pithy way of saying it. You've all probably heard this, for every action there will be an equal and opposite reaction. That has to do with the third law. And this says the internal forces that parts of a system exert on each other will always be balanced. This means a closed system can't change this motion without an external force. And so we have a system that consists of objects A and B, and they exert forces on each other. In this particular case, B is pushing on A to the left, and A is pushing on B to the right. And as you can see, these force vectors are exact opposites of each other. They are negatives of each other. They have the same size, but they are pointing in opposite directions. And so one statement of the third law is that when you have a system like this, then the force that A exerts on B will always be the negative of the force that B exerts on A. And an equivalent way of saying this is that the sum of the internal forces of a system always adds to 0. Okay. Now, so in summary, there are essentially 3 equations that you need to know to work with the 3 laws. The first equation is that the net force will equal 0 if the acceleration is 0. The next equation is that when the acceleration is not 0, the net force will equal m times a, the mass times the acceleration. And finally, if you have 2 objects exerting forces on each other, if object A exerts a force on object B, there will always be a companion force that B exerts on A, and those forces will always be negatives of each other. They'll always be equal and opposite. And as I said earlier, these laws were considered counterintuitive, especially the principle of inertia, because the expectation before was that rest was the normal state, and motion was an exception to rest caused by external forces. And Newton is claiming that motion is the default behavior of objects in the universe, and that acceleration is caused by external forces. So what this means is that motion does not require force, according to Newton. And that is extremely counterintuitive to most people, even today. So we're going to go through some important forces. The first force is the force of gravity. And there are 2 forms for the force of gravity law that I'm going to talk about. The first one is computing the force of gravity based on the local gravitational field. So the gravitational field is just the acceleration caused by gravity within a particular region of space. Okay, so for instance, we know near the surface of the Earth, gravity causes an acceleration of 9.8 meters per second squared towards the center of the Earth. Now, as you get further away from the surface of the Earth, that acceleration diminishes and becomes weaker. Okay, so the acceleration due to gravity depends on where you are in space relative to other massive objects. And so sort of the local form for computing the force of gravity is determine your local acceleration due to gravity. That's called the gravitational field. Multiply that acceleration by the mass of the object you're interested in, and that gives you the force that is acting on that mass to produce that acceleration. Okay. And so here I have a picture of some object with a certain amount of mass, and it has a force of gravity pointing down towards the center of the Earth, and I have drawn the gravitational field, which would be the sort of the acceleration an object would experience if it was placed at that location in space. Down here on the bottom, we have the Newton's universal law of gravitation. And this is kind of an explanation of where the gravitational field comes from in the first place. And so on the bottom, Newton hypothesized, and it turned out to be true, that the magnitude of the force of gravity between two objects is based on the amount of mass they have. So the hypothesis was that every object which has mass exerts a gravitational influence on all the other objects which have mass. Okay, so you have mass, your friends have mass, you and your friends all exert the force of gravity on each other. Okay, the Earth also has mass, so it exerts a force of gravity on you, and you exert a force of gravity on the Earth. You usually will not notice the force of gravity due to anything other than the Earth, because the amount of mass that you and everything else on the Earth has is pretty minuscule compared to the Earth's mass. So the Earth is so extremely massive that on the Earth we pretty much only notice the mass of the Earth. But if you do very careful experiments, you can demonstrate that all objects exert a force of gravity on each other that's trying to pull them together. And so Newton postulated that this force magnitude would be proportional to the product of the masses of the two objects and inversely proportional to the square of the distance between them. And the proportionality constant is called Newton's gravitational constant. You can look up the number in a book. I can't remember it off the top of my head. I think it's like 6.67 times 10 to the negative probably 13 or something like that. But you don't need to know the number for now. This is just a constant number. And these are the masses of the two objects exerting a gravitational force on each other. And this is the distance between those objects squared. Here in the diagram, I show a picture where I have object A and object B. They each experience a force of gravity, which is the same amount for each of them. And that force of gravity points along the line connecting the two objects, so it's trying to bring them directly together, if it can. And I've drawn the distance between the objects, R, A, B. Okay. Next, we're going to talk about Hooke's Law. Hooke's Law is an extremely important law. If you guys are going into engineering, particularly anything that involves structures and materials, you're going to be probably working with some version of Hooke's Law. It may not be as simple as this version, but this is a pretty universally important law for materials that are subject to forces that create small displacements in their internal pieces. And so what Hooke's Law says is that when a spring is displaced from equilibrium, it will experience a restoring force that tries to restore that equilibrium. So I've drawn a spring in three different situations. This is a spring just at rest. It's not being stretched or compressed. And above it, I show a spring which has been stretched from equilibrium. And D, this displacement factor D, represents the displacement from equilibrium. And Fs here is trying to pull that mass back so the spring won't be elongated anymore. In this case, the spring has been compressed, so the displacement is to the left, and the spring force is pointing to the right, trying to bring that object back to the equilibrium length of not being extended or compressed. And so Hooke's Law simply says that the restoring force is proportional to the displacement from equilibrium, and it points in the opposite direction. So the restoring force will always be opposite to the displacement from equilibrium, because it's trying to put you back towards equilibrium. That's what the negative sign means. And K is called the spring constant, and sometimes it's called the spring stiffness. If you're talking about like a material, like a structure, then the structure would have something called a stiffness matrix that would correspond to that K. And so I guess I should write K as spring constant. And K always has units of newtons per meter. And that is Hooke's law. It's just a statement that these displacements are proportional to the amount of force that is trying to undo them. The normal force is a special kind of contact force, and the normal force basically is the name for any force that prevents you from going through the surface of an object. Okay, so if you're like sitting on the couch, then the couch is exerting an upward normal force to prevent you from falling through the couch onto the floor, and the floor is exerting an upward normal force on you to keep you from going down to the center of the earth, and so on and so forth. By definition, the normal force is always perpendicular to the surface itself. So when we talk about contact forces, there's two kinds. There's contact forces always arise from being in contact with a surface, and those forces can either be perpendicular to the surface or parallel to it. The component of the contact force that is perpendicular to the surface is always just called the normal force, and that's always just preventing you from moving through that material. Any component parallel to the surface is a frictional force, and that's always going to try to prevent you from sliding across the material, either starting to slide across or continuing to slide across. And so here I've drawn an inclined plane with a mass sitting on that plane, and we have the force of gravity pointing down and a normal force pointing perpendicular up and to the left to prevent this mass from falling through the inclined plane. You should be able to see that these forces are not balanced. If I add them together, I can't get zero because they point in different directions, and there's only two of them. So this object will accelerate, and what it's going to do is it's actually going to accelerate this way because the external forces acting on it are not balanced per Newton's second law. Okay, next we have friction, and there are two kinds of frictional forces we are going to be interested in. The first is called static friction, and this only applies to objects which are not already in motion. So this prevents objects from starting to slide across the surface. The notation for static friction is going to be F with a subscript Fs for friction static, and the force of static friction is simply always going to point in whatever direction it needs to point to prevent an object from sliding across the surface. So for instance, I have a mass here. There's a 5 Newton force. Maybe some person is pushing on this block to the right with 5 newtons of force. And a force of static friction is pointing to the left to oppose that, so the block will not start to slide across the surface. Okay. The static friction force obviously has to have some limit because it is possible to slide objects across surfaces. And so there's something called the maximum static friction, which is the largest amount of static friction that a surface can exert based on the two materials that are in contact. The maximum static friction is always going to be a friction coefficient called mu sub s, or the coefficient of static friction, times the magnitude of the normal force exerted on the object. The coefficient of static friction depends on the type of materials in contact. So, for instance, you'll have different numbers for this depending on if it's like wood on steel, or steel on copper, or gold on iron, and so on and so forth. Um, let's see, iron on rubber. Uh, so every type of materials that can be in contact will have a different number for the coefficient of static friction. And Fn is just a measure of how much force that surface is exerting to prevent the object from moving through it. And you can kind of think of this as a measure of how hard the object is being pressed into the surface. And so, as you might imagine, if the object is really hardly pressed into the surface, it's going to be hard to slide it. But if it's only gently resting on the surface, it's very easy to slide it across the surface. So it makes sense that the normal force would show up here for the maximum force of static friction. So basically, as long as the other forces acting on the object don't produce a force greater than that maximum static friction force, then the objects will not slide. As soon as they exceed it, the objects will start to slide across the surface. Once an object starts sliding across the surface, kinetic friction kicks in. And this is the force of friction that acts on an object which is already sliding across the surface. The force of kinetic friction is always going to be less than the maximum force of static friction. And there is a friction coefficient which encodes that, and that's called the coefficient of kinetic friction. And in this case, the force of kinetic friction is equal to the force coefficient of kinetic friction times the normal force. So this should look kind of familiar to the formula we had for the maximum force of static friction. But the important thing to realize is that here we have an inequality, so it's not always equal to, it simply cannot exceed that number, whereas over here with kinetic friction, it's just always equal to that number. So the force of kinetic friction is just equal to E sub k times Fn in magnitude, and the direction of that kinetic friction force is always going to be in opposition to the motion. So I have this picture of a block which is sliding to the right across the surface at a rate of 30 meters per second, and because it's moving to the right, the force of kinetic friction has to point to the left to oppose that motion. And so the force of kinetic friction's goal is to bring the object back to rest. And this is, of course, why the ancients thought that rest was the default state of motion, because frictional forces are acting on everything, and they're always bringing things back to rest relative to the... Tension is a force transmitted along the length of a string, and it always is going to be parallel to the string itself. So when you pull a string taut, that's when you're going to be seeing this tension force, and it prevents the string from being elongated further than a certain amount. So once you've got a string to the point where it's taut, the tension prevents you from stretching it further, and it's always transmitted from one end of the string to the other. The force of tension I've drawn here in a couple of different circumstances will always be the same throughout the string, provided that the string does not have a significant amount of mass. And so we usually refer to the idealized case as the case of the massless string. Okay. Force has units of newtons, and you can figure out what a newton is in terms of more familiar units by using the kind of basic equation for force provided by Newton's second law. So what I have here is kind of a baby or simplified version of Newton's second law, and I go ahead and put 1 newton in for the force, 1 kilogram in for the amount of mass, and 1 meter per second squared for the amount of acceleration. And when you work that out, you find, okay, well, 1 newton then must equal a kilogram times a meter per second squared, or a kilogram meter per second squared. And as long as you're working in SI units, kilograms, meters, and seconds, you'll always get newtons out when you arrive at a force. Our first example is going to be a determination of mass from a known force and an acceleration rate change in velocity. This is a way that you would measure mass if you couldn't use a scale, maybe because the force of gravity might be different because you're on the moon or in outer space or something like that. So an object with an unknown mass, m, is initially moving to the right at a rate of 100 meters per second squared. A constant 5 newtons of force, which points to the left, acts on this object for 10 seconds. The final velocity of the object is 90 meters per second to the right. What is the unknown mass, m? Well, I'm going to make a list of knowns, unknowns, and equations. And so we'll start with what we know, which is the initial and final velocities, the amount of time that the force acts for, which is also the amount of time to change the velocity by that amount. And we know that the external force which causes this acceleration is 5 newtons in magnitude. The acceleration is not known, and the mass is not known. We do know that Newton's second law will apply here, and the net force is just the external force itself. And we know that acceleration is computed by taking the change in velocity and dividing by the amount of time. So I start with the definition of acceleration. It's delta v over delta t. The delta v is negative 10 meters per second, and the delta t is 10 seconds. And so my acceleration is, I got a typo here. It's negative 1 meter per second squared. And if I work with just magnitudes, that works out to 1 meter per second squared of acceleration. The Newton's second law tells me that the net force equals ma, and the problem tells me that the net force is just the external force. And so I get that ma is equal to the external force, and I'm going to just compare the magnitudes of those, the left-hand side and the right-hand side, because it's basically just a one-dimensional problem. So ma equals the external force. So ma is the external force. That means m is the external force divided by a. A is 1 meter per second squared. And so 5 newtons over 1 meter per second squared is going to be 5 kilogram meters per second squared divided by 1 meter per second squared. And you can see that these guys cancel each other, leaving me with just 5 kilograms. And so that is the amount of mass determined from the acceleration and the amount of force. You can see that the mass is inversely proportional to the produced acceleration. So basically, a large mass would be something that had a very small acceleration. It's not easy to change the velocity of a really massive object. And small mass would correspond to a very big acceleration. So it is very easy to change, say, the velocity of a ping pong ball, which doesn't have much mass at all. So that's just something to kind of keep in mind when you're looking at this equation. That kind of for a fixed external force, we actually change the axes here. If I'm using F equals ma here, then there's sort of a hyperbolic relationship here where large mass means small acceleration and small mass means big acceleration. Okay. Example 2. A 6 kilogram object is at rest on a table. What is the magnitude of the normal force acting on this object? So here I have a picture of what's going on. A 6 kilogram object is sitting on the table here, and the force of gravity is trying to pull it through that table. And the normal force is the table pushing back on that object, pushing on it so that it does not go through the table. So force of gravity and the normal force are both acting on the 6 kilogram object. And I'm going to represent that by drawing what's called a free body diagram. A free body diagram is a picture or a diagram where you simplify the situation. You represent the object of interest, in this case the 6 kilogram object, as just a single point. And you draw all the forces acting on that object as vectors emanating from that point. And so this is an example of abstraction where you remove extraneous or unnecessary details from the problem so that you can focus on only what really matters, which is that there's two forces acting on one object here. Newton's first law tells me that because this object is at rest, and therefore not accelerating, that the net force had better equal 0. So what that means is that when I add these force vectors together, I'd better get 0 as my final answer. So I can take Newton's first law, and I can expand out the sum and say, well, the sum of the forces is just the normal force and the force of gravity being added together. Those had better add together to be 0, which means that the normal force is the negative of the force of gravity. And then if two forces are negatives of each other, that means that they have the same magnitude. So the magnitude of the normal force is the same as the magnitude of the force of gravity. And then I just substitute in mg for the force of gravity, because I know that's what it is. And I get that the normal force's magnitude is equal to mg. So now I just take the mass of the object times the acceleration due to gravity, and I determine that that is 6 kilograms times 9.8 meters per second squared, assuming I'm on the surface of the Earth, and I get 58.8 newtons for the amount of for the magnitude of the normal force. Now, something I want to warn you about is that the normal force in general does not equal mg. This is really only for situations that are kind of very simplified, where the only vertical force that is perpendicular to the surface is the force of gravity itself. So the normal force does not have to equal mg, and in fact, I can give you millions of cases where it will not equal mg. But this is usually kind of the first example people ever see with the normal force, and they think that this step right here is like a formula, but it's not. It's just a particular solution to this problem. Just as an example, if I go back real quick, if I had an inclined plane with a mass sitting on that plane and the force of gravity points down and the normal force points outward, then in this case the normal force would be mg cosine of theta. Okay, so the normal force does not in general equal mg. Okay, example 3. An object is supported from the ceiling by two strings, as shown in the picture. It is initially at rest. What is the magnitude of the tension in each string? So I know that it is initially at rest. It is at rest. So it's not initially at rest, it's just at rest. And because the system is at rest, I know that the net force had better be 0. And I have a picture here where I have string A and string B drawn here. And there are forces of tension which point parallel to those strings. The force vectors are not necessarily the same length as the strings. In fact, they're definitely not. Tension A, or string A, makes an angle of theta with the horizontal, and tension B makes an angle of phi with the horizontal. There's also the force of gravity that is pulling the mass down towards the Earth. And I want to determine these forces in terms of the angles and the mass and the acceleration due to gravity. So I make a free body diagram. I represent the mass as just a single point at the center of the free body diagram. I draw my tension forces, and I decided to just represent those as FA and FB in this picture. So FA is the tension in string A, and FB is the tension in string B. and then the force of gravity just points straight down. I've drawn coordinates, an x and y axis, to indicate which way the x-axis points, which is horizontal, and the y-axis is vertical. I want to impose the equation that the sum of the forces equals 0, but this looks a lot more complicated than the last problem, right? So before, I just had two forces, normal force plus force of gravity is equal to 0. Now I have three, and they point in all sorts of different directions. And so to handle that, what I'm going to do is I'm going to make a force chart where I break up the components of each force along the different dimensions of space. Here, I'm going to informally write FA, FB, and FG to represent the magnitudes of these force vectors, rather than constantly writing like the magnitude of FA. I'm just going to write FA. And this is a convenient shorthand that will save a lot of time in writing the equations. Let's get into the components. So for the x components of my tension forces, the first thing you should notice is that the angles are adjacent to the horizontal direction. So that means I'll use the cosine to get the x components. And those angles are opposite to the vertical direction. So I will use sine to get the y components. The tension A points up and to the left, which means a positive y component and a negative x component, which is why this is positive and that's negative. Tension B points up and to the right. Those are both positive components. So I get a positive x, sorry, not there, a positive x component and a positive y component for B. And obviously tension B involves the angle phi, and tension A involves the angle theta. So you can see there's a lot of symmetry between these two vectors in terms of how I treat them. The only real difference being this negative sign here. Then when it comes to the force of gravity, the force of gravity points straight down, so there is no x component. It doesn't point to the left, and it doesn't point to the right. So the x component is 0 newtons, but the y component is negative Fg. Negative because it points down, and Fg because the entire magnitude points down. And so those are all the different components of my various forces. Now I'm going to impose Newton's first law. So Newton's first law says that the sum of the forces adds up to 0. But that translates directly into the sum of the components add to 0 for all the different forces. And so if I look at the sum of the components for the x forces, then I would have negative FA cosine theta plus FB cosine phi, and then really plus 0 for the force of gravity. And that is going to equal 0 according to Newton's first law. Then, when I add the y components together, which is literally just this plus this plus this, I am going to get FA sine theta plus FB sine phi plus negative FG, or just minus FG, and that's going to equal 0. And finally, we have the formula that says the force of gravity on the surface of the Earth is the mass of the object, this is an m, times the acceleration due to gravity. And those three equations need to be solved in order to determine FA and FB, which is my ultimate goal. So this is where the physics is. The actual solving of these equations is what we would consider the math, right? This is where physics and math go their separate ways. So physicists are usually more concerned with figuring out what the correct equations are, and mathematicians are more involved with, well, how do you actually solve those equations? And of course there is an overlap in practice, but I'm just kind of saying this is where the boundary between the two disciplines lie strictly. So I'm going to show you how to solve this system of equations, but I'm going to show you how to use technology to do it. Because you've probably learned how to solve systems of equations in your algebra classes, but you may have not learned how to use technology to do this. So I'm going to show you a computer algebra program called WX Maxima. And this is a program that can do math for you. And this is like a professional quality software. So it can handle quite a lot. So I'm going to define three equations. So I'm going to have like equation 1, equation 2, and equation 3 that I'm going to define in here. And to define an equation, I type its name, like equation 1, and then I put a colon. The colon says everything to the right is going to be the definition of what this equation is. And so my first equation is going to be this guy right here. The sum of the forces in the x direction set equal to 0. And so that is going to be the negative of force A times the cosine of theta. So negative, type that here. Negative of force A times the cosine of theta plus force B times the cosine of phi. And that's going to equal 0. Equation 2 is going to be force A times sine of theta. I'm going to be doing the sum of the y components equal to 0. Force B times sine of phi minus force of gravity. That's equal to 0. And equation 3 is just the formula for computing the force of gravity in terms of mass times the acceleration due to gravity. Okay, so I've just defined my three equations, and then I want to use what's called the solve feature. So there's a syntax for it, but I would also want to point out you can actually just go up here to equations and type solve, and then it'll just say who are your equations. Well, my equation 1, equation 2, and equation 3. Notice I'm putting commas between these. And then I'm going to put the variables that I want. So that's force A, force B, and the force of gravity. And then when I hit OK, it's going to give me the solution to those equations. And it gave me something I didn't expect, which is an empty bracket, which means I may have typed something wrong. So let me go back up here. Let's see. What did I type wrong? Equation. I see it. So I dropped my underscore when I was typing equation 2. So I made a typo on this guy. Now that should be fixed. And so to re-enter this command, I'm just going to type Shift-Enter, which is how I entered all these commands up here. Once I finish them, I just type Shift-Enter. And now I have the solution to my equations. Sometimes it won't give you a simplified solution. This is simplified, but if it doesn't, you would just type ratsimp, and then you would type the label for the output, which in this case is %05. And you can see that %05 right here. This is input 5, output 5. Input 7, output 7. It tried to simplify, but it couldn't find anything to simplify, so that is the final solution. And so now it's done all the algebra for me, and I've got the solution to my equations. So now I can just go to the next page, and those are my solutions. Something I want to point out is that the answers for the tensions in string A and string B are highly symmetrical, and that's because this is a highly symmetrical system. The only difference between string A and string B is an exchanging of the two angles, right? So if you swap the angles, you would swap which string you're talking about. Um, and this is going to be the final example for today, and there will be more examples released this week. You'll also, in the near future, be getting a lab where you can kind of try out WX Maxima and learn how to use it. So hopefully that it can help you solve problems in your homework and on exams. You're certainly allowed to use WX Maxima in this class. It's kind of like a fancy supercalculator, because all it can do for you is math. It can't actually formulate a physical problem for you. Okay, so that is it for WX Maxima.